Hello guys, good evening. Am I audible? Yes, few more minutes, we'll start. Two minutes, guys. Okay, so what have we done last class? Effective nuclear charge we have done. It's still the last topic we were discussing. I think we had discussed the atomic radius, correct? Okay. So all those covalent radius, van der Waals radius, we had discussed. Have we discussed ionic radius? Okay. So write down the next topic. That is ionic radius. Obviously, as the name suggests, it is defined for ions, right? So write down, it is the distance between it is the distance between the nucleus and outermost shell of an ion. Shell of an ion. Okay. Okay. So if you have any atom, an atom can have positive or negative charge, or it can be neutral also, right? So if you have the cation of an atom, then the radius of cation is lesser than the radius of that atom. For example, if I take R of Na plus, it is lesser than to that of Na atom. This is what it means. Similarly, if you talk about the radius of an anion that is negatively charged is greater than the radius of an atom, which means again RCl minus, if you are taking, it is more than the radius of a chlorine atom. Right? So like atomic radius, ionic radius also decreases down the group. So as we go down the group, ionic radius increases. Same reason, extra shell is getting added, so ionic radius also increases. In this, one more term that we use, and this we call it as isoelectronic species. Isoelectronic species. Write down, these are the ions or atoms are the ions or atoms which has equal number of electrons. Hence it is isoelectronic species. Equal number of electrons. Right? For example, we have N3 minus, N3 minus, O2 minus, F minus, okay, like Al3 plus, Mg2 plus, Na plus, all these are isoelectronic species. Copy this down. Okay, so tell me the number of electrons present in these ions. No, it's not like that, Shitish. If you are adding an electron to the shell, the electronic repulsion is more over there. That's why Cl minus ion will have more radius. You are only considering one factor, that is electronic attraction towards the center. But we have at the same time we have electronic repulsion also. Okay. So electronic repulsion dominates and hence has more, ionic radius for Cl minus. You are adding an electron in the shell, right? So obviously that will increase the repulsion, no? Z effective sigma value increases. Status spinning constant. Hence Z star decreases. All these ions have same number of electron, that is 10. Okay. Now write down in isoelectronic species, write down in isoelectronic species, or write down like among iso, not in, among isoelectronic species, isoelectronic species as the magnitude of negative charge, after this write down 1 point, as the magnitude of negative charge increases, size means ionic radius decreases, right? So for example, if you have to compare N3 minus, O2 minus, and F minus. Oh, I have written it this way, size increases, not decreases. Okay, as the negative charge increases, size increases because you are adding more electron into it, right? So among these three ions, all these three are isoelectronic species, and the size order is this, right? Similarly, as the magnitude of positive charge increases, size decreases. More positive charge, size decreases. So for example, if you have Na plus, if you have Na plus, then Mg2 plus and Al3 plus, the order of ionic size is this. Done? There are some exceptions in this. It is not for isoelectronic species, but regarding the atomic size, there are some exceptions. Okay, and the exceptions are what? You see these three order I'm giving you. You memorize these three order. Okay, it has been asked in the exam, and these are exceptions. Okay, so few exceptions we have into this one. I'm not talking about isoelectronic species here, but general, the ionic size. Okay, F minus is lesser than Cl minus, which is even lesser than H minus, hydrogen minus. Then we have F minus is lesser than O minus 2 is lesser than H minus. Al3 plus is lesser than Mg2 plus is almost equals to Li plus less than K plus. Even Mg2 plus is slightly higher than Li plus also. So lesser than equal to we can consider here, right? So these three are exceptional ionic size, okay? Ionic size or ionic radius. These three you must remember. Among these three, this one they have asked in JEE exam. These three order. Done? Yeah, that's what I said. This is an exception. Okay, when you add an electron in hydrogen, the decrease in Z effective is exceptional over there, and that's why we have exceptional trend. It is based on the the actual ionic radius that we have, the values, right? So you have to memorize this. Hydrogen is the smallest element we have, but H minus is bigger than Cl minus. That is because of the exceptional decrease in Z effective. Okay. Now, the next thing you see here, the next term that we are going to discuss, that is, write down ionization enthalpy. Ionization enthalpy, we also call it as ionization potential, right? Ionization potential or ionization enthalpy, both are the same things. IE is the ionization enthalpy, IP is the potential. Ionization potential, and both are the same thing. Definition of this you write down. It is the amount of energy required to remove an electron amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Okay, amount of energy required to remove an electron from an isolated gaseous atom. Okay, isolated gaseous atom is important. Okay, so for example, suppose we have an element M, gaseous element, and when you provide ionization energy, IE, it converts into M plus gas and one electron goes out. Right? Since it is removing the outermost electron, the first electron, we call it as first ionization potential. Okay, IE1 in fact it is. IE1. Similarly, again you remove the second electron from this, M plus, IE2 you provide, it converts into M plus 2 gas plus one more electron. Okay, so this is first ionization energy, second, then third, fourth, fifth, and so on. So could you tell me the relation of IE1, IE2, IE3, IE4, and so on? What is the order? Which one is maximum? IE1 is the least and IE4 is the most. And why is that so? Because as the electrons are going out, yeah, we are moving closer to the nucleus and hence more interaction, more attraction. Okay. So for example, you see sodium, if I take an example of sodium, the electronic configuration is gaseous atom I am considering, and we provide IE1 here. It converts into Na plus gas and one electron goes out. The configuration of this atom, sodium, is 1s2, 2s2, 2p6, and 3s1. So IE1 you are providing means you are removing this particular electron. For this one, the configuration is 1s2, 2s2, 2p6. Now further you see, if you want to remove an electron again, you are going to remove an electron from the completely shelled, exceptionally stable configuration, right? That is the inert gas configuration we have. So IE2 is extremely high here because you want to take an electron out from a very stable configuration. This ion does not want to lose its electron easily, right? That's why we have to provide a very high amount of energy here, IE2, right? And it is very difficult to remove an electron from this, which is not possible under usual condition. That's why this further thing is not possible. But yes, if somebody asks you what is the relation of IE2 and IE1, IE2 is greater than IE1. In fact, it is true for in normal cases also. Right, in this case it is getting an inert gas configuration, but in normal cases also it is true. Whenever you are removing an electron, right, then the size of the atom is decreasing, ions are decreasing, and the outermost electron becomes more strongly attractive, towards the nucleus, and it is difficult to remove that electron. Got it? So that is what the order we have. Okay. So this is ionization energy. amount of energy required to remove an electron from the isolated gaseous atom. Now, what all factors we have which affects the ionization energy? Write down factors affecting it. Factors affecting it. First one, the size of an atom. What is the relation we have? As the size increases, ionization energy increases or decreases? Size increases, ionization energy decreases, not increases. Yeah, it should decrease. So ionization energy, IE, write down, it is inversely proportional to the size of an atom. Okay, size of an atom. Now the second factor is write down effective nuclear charge, Z effective. Could you tell me the relation in this? Effective nuclear charge with ionization energy. More effective nuclear charge means electrons are strongly attracted to the nucleus, and hence we say what? That ionization energy is directly proportional to Z effective. Let me know if you have any doubt in all this. Okay, there are many things to memorize in this particular chapter, so, right? Those things which you can understand, you must understand that. Okay, everything you cannot mug up simply. Okay, next, write down shielding effect, screening effect or shielding effect. Write down the screening effect. The screening effect reduces the force of attraction reduces the force of attraction between the electrons and the nucleus. And electrons means we are talking about outermost electrons here, right? Because we are talking about ionization enthalpy. Decreases the force of attraction between the outermost electrons or electrons and the nucleus. Hence, the removal of outermost electron becomes easier. Hence, the removal of outermost electron becomes easier. Hence, what we can write, the ionization energy that we have, it decreases as screening effect increases. So, inversely proportional. the screening effect. Okay, so this is the order we have here. Next, fourth one, write down. Write down the penetration effect of orbital. Penetration effects of orbitals. Okay, write down into this. Now, the ionization enthalpy or energy increases as the penetration effect increases as the penetration effect why the number is so less today? Any specific reason? Do you have any kind of exam, unit exam or something? I can see only 11 of you. Oh, that's what I thought. I got it actually. Yeah, I can feel that you are low actually. This thing we are experiencing from the last 3-4 years. Whenever in the school there are exams going on, the number dropped in the class. Every time it happens. That's why I thought that number is less. Usually we had around 16, 17 students, right? I can see it is 11 only today. So I thought maybe your exam. Anyway, so what exam you had today? What paper? Maths. How was it? Good? Very good. So what is your expectation out of, like, it was 25? No, I think unit test is for 25 marks, I guess. 30. Okay, 30. So how much you are expecting out of 30? 25 plus all of you? All of you 25 plus? Okay. Happens, Ruba. In exam it happens, like, these are the learnings actually with the exam only you get. Not an issue. When you have chemistry? Day after. Portions? First two. Mole concept and atomic structure? Yes. Okay. I hope you'll do well. Okay. Fine, not an issue. Okay, let's continue. Penetration effect. Write down. Uh, you wrote the first line, no? The ionization enthalpy increases at the penetration effect of the electrons in the different orbital increases. Okay, again I'm repeating this. Ionization enthalpy increases as the penetration effect of electrons in different orbitals increases. Okay, so basically penetration effect is because of the shape of the orbital. Okay, because of the shape of the orbital, the electrons has, attraction towards the nucleus. Okay, so it has been observed that if the electron is present in s orbital, it has the maximum penetration effect it shows. Then p, and then d, and then f. This is also experimental order we have. Okay, penetration effect. This means what? What do you mean by this? This means, suppose you have two atoms And if you have to remove an electron from S shell of one atom and P of the other atom, then you have to provide more energy when you remove an electron from the S subshell, right? So in this order, the removal of electron becomes difficult, SPDF, right? Like for example, I'll show you this one. Suppose we have magnesium, okay? Let's take this example. We have magnesium and we have one more, that is aluminium. Give it a try. Tell me which one has more ionization energy, magnesium or aluminium? Magnesium. And why magnesium? Yes, there are many explanations actually that you can do with. Okay, one is, you know, magnesium is towards the right, sorry, aluminium is towards the right, okay, of magnesium, right? And we also know as we go left to right, the size decreases. So aluminium has a smaller size, sorry, left to right, if you go, size decreases, right? So aluminium has a smaller size than magnesium, correct? So if you look at this particular theory, then which one should have the maximum, this thing, which one should have the more ionization enthalpy, magnesium or aluminium? See, what I'm trying to make you understand, yes, correct. Your answer is correct, first of all. Magnesium, your answer is correct, okay? But logic is not correct, Kshitiz, okay? I am just trying to make you understand two factor here, which is actually the nature of inorganic chemistry. Probably you will understand from this example, okay? Like when I said there are multiple factors and the final result that we have, it depends upon the dominating factor that we have. This particular point you can understand with this example very easily. You see, if I talk about the atomic size, obviously aluminium has lesser atomic size than magnesium. Left to right we are going. It has more Z effective, lesser size than magnesium. Size factor, if you are considering, I'm telling you here, I have already told you here that first point you see, ionization energy is inversely proportional to size. So if you consider the size factor, then aluminium should have more ionization energy than magnesium. But that is not the answer. The answer is what? The answer is ulta, right? The other way. Okay. Answer is this of ionization energy order. Okay. So one factor gives you aluminium as the answer. Another factor, what is the factor? That is a penetration effect, gives you magnesium. So here also again, there are two contradictory factors here. That's why I said that final results depends upon that which factor is dominating. And for exams, for to get the correct answer in the exam, you should know that where you have to apply what factor dominates. And that is the difficult part here. There are so many things. It's very difficult to memorize all these things and keep in mind that here you have to think of this particular factor and here you have to think of this particular factor. Okay, that is a bit confusing and problem with inorganic chemistry. But yes, it is there for everyone, right? So you have to revise it again and again. No, we cannot say that. It depends upon the condition and everything, right? So there are so many factors we have. So you see this magnesium, why the answer is this? Because if you look at the outermost electronic configuration, it is 3s2. Outermost is 3s2. And for this one, it is 3s2, 3p1. So if you want to remove an electron, okay, from outermost shell, so for aluminium, you are removing from p subshell, and for magnesium, you are removing from s subshell. S subshell has more penetration effect, hence the order is this. Correct? I hope you understood this. Now, if I ask you this question, for example, if I ask you Mg plus and Al plus, Okay. What is the order of ionization energy? Which one has more ionization energy here? Now it's Al. Why? Yes. So what happens once you remove this, the configuration becomes what? It becomes 3s1 and it becomes 3s2. So both are in the same subshell. Now we consider the electronic configuration here. So this one is completely filled, more stable, right? Hence the order is more stable, plus size also is one of the factor. So hence overall order is this, right? So it depends upon what configuration you have. So all these factors you must keep in mind, okay? Uh, and try to understand that where you are applying what factor. Okay, that's the one thing. Next one you write down, the last factor here, the fifth one. Uh, Stability of half filled and fully filled configuration. Okay, we know half filled and fully filled are more stable configuration we have. So if you have this order, you remember, if you have D5 configuration, then ionization energy will be least. D5, then we have P3, both half filled. Then we have D10, fully filled. Then we have P6, fully filled. Okay. Why P has more than D, both half shell? Because we know P has more penetrating power, right? Order we have seen. P fully filled has more than D. Again, P has more penetrating power. It is this. D10 configuration is slightly more stable than P3, and hence the order is this. Okay. So these are the few factors we have which affects the ionization energy, right? And you must remember this factor when you get the question. You have to think of all these factors depending upon the question, and then you can write down the answer. We'll discuss that, Shitish. It's not like always we have ionization energy. There are so many exceptions into this. We'll discuss that. Along a period, if you go, then what happens? Along the period, if you see, then in each period, noble gas has the highest ionization energy. Here also, I'll tell you one thing, okay? Few points you write down first of all, the trend of ionization energy. It is important, right? Because we can conclude or understand so many properties of the elements with the help of ionization energy. Okay, write down the trend of ionization energy. As we go left to right in a periodic table, as we go left to right in a periodic table, the ionization energy, I'll write down just a second. Left to right in a periodic table, ionization energy increases, but will have some exceptions, with some exception. What is that exception? We'll see. With some exception. Okay. Top to bottom in a group, ionization energy decreases because the size is increasing, right? And when we write only ionization energy, you should take it as first ionization energy. Yes. So should just go on. Which one, Pradyun, you are talking about? That's what I wrote. I wrote over there with some exception. Okay. I'll explain this. Just give me some time. Okay, I'll explain this. Okay. So this is the general trend we have. Left to right, ionization energy increases. Okay. Now, what are the exceptions we have into this one? Okay. The exceptions are, like, suppose if you talk about lithium and beryllium, right? So which one has more ionization energy, lithium and beryllium? Should be beryllium, right? So if I'm talking about period 1, you see this. First period, that is hydrogen and helium, right? Hydrogen and helium. So obviously helium has more ionization energy than hydrogen. Why? Because it has the more stable configuration, right? If you talk about period 2, the order is, we have lithium minimum, then boron, then beryllium, then carbon, oxygen, nitrogen, fluorine, and then we have neon. This is the order we have. There are a few changes here, you see. The first change is this, boron to beryllium. Ideally boron should be more than beryllium, but we have this order. And the second one, it should be this. Why this is happening? Because nitrogen has fully filled configuration. Half filled configuration. 2s2, 2p3. This one has 2s2, 2p2. So half filled configuration, it is more stable, hence difficult to remove an electron from this. Neon has fully filled configuration, 2s2, 2p6, hence maximum ionization energy. Similar thing we have here also. Beryllium has 2s2 configuration outermost, and this one has 2s2, 2p1. So always you see penetration effect, S is more than P, so we have this order. So these are the few exceptions we have in period 1. Copy this down. 2s2 is more because 2s2 is closer to the nucleus, more ionization energy. 2s2 and 3s2, if you compare, 2s2 is more. Done? Yes, oxygen is 2p4, correct. I written 2p2 by mistake. It is 2p4. Done, all of you? Right, general trend you must know, but general trend generally they don't ask in the exam. They'll ask you these variations like, no, where we have some exceptions, half filled configuration, fully filled configuration, and other things, right? So these changes that you have, this you must take care of. Okay. Now, another thing is, you see, the third one in this, if you talk about copper, Ag, and Au, do you have periodic table with you? Do you have periodic table? Yes. So you can see copper belongs to which period? Fourth period. And this is 3D series element. Yes or no? 3D series. Because the D block element you see, the first one is 3D, then 4D, and then 5D. Correct? Like this we have 3D, 4D, and 5D. 3D series, 4D series, and 5D series. And in the last we have zinc, and before zinc we have copper. And below copper we have Ag, and here we have Au. Yes or no? Could you check that? Yes. So this is 3D, this is 4D, and this is 5D series element. 3D, 4D, and 5D series element, correct? So as you go down the group, what happens? Ionization energy decreases, correct? So order should be what? Copper is maximum, then Ag, and then Au. This should be the order, right? But this is not the order we have. Okay. In this, gold will have the maximum ionization energy. So order is, all these are exceptions I'm giving you. Maximum ionization energy, order is, gold has maximum, and then we have copper. So Ag is the minimum, we have like this. I'll tell you the order here exactly. We have minimum for Ag, then we have Cu, and then we have Au. Why Au is maximum? It is because of lanthanide contraction. It is because of lanthanide contraction. Got it? Copper is more than Ag, so this order you must remember. This is 3D, this is 4D, and this is 5D series. Right? Even in D block, what you have to memorize? No, it's Au is not transition. You can say transition also, but better is to use lanthanide contraction, because before Au, the F block elements, the F substance are also filled, right? So it is mainly lanthanide contraction because lanthanides are present before Au. That's why we are using the term lanthanide contraction. Okay. Only 5 means what? It is 5 and below means what? Fifth group, fifth period. Yes, generally for fifth, the lower elements that you have, that is fifth period, before that only will have transition contraction. Basically, when the elements are present before lanthanides, then it is transition is the better word to use. Otherwise, we use for sixth and seventh period, we use lanthanide contraction. Okay. So for D block, what you have to memorize here, we know in D block we have 10 groups, right? So for group 3, the elements of 3D series, 5D series has least, then 4D, and then 3D series we have. Order of lanthanide, ionization energy is this. If you have group 4, 5, 6, and 10, the order is 3D series has minimum, then 4D, and 5D has maximum here. If you have group 7, 8, 9, 11, and 12, right? It is 4D has minimum, then 3D, and then we have 5D. This is the order we have, okay? This you have to memorize because like I said, there are multiple factors. We have electronic repulsion, we have lanthanide contraction, we have transition contraction, shape of the orbital, right? That's not a major factor here, but yes, there are multiple factors. So based on all these factors, the overall order is coming out to be this, right? So this you have to memorize. Group 3 for this, 4, 5, 10 for this, 7, 8, 9, 11 for this. Where we have 10, 4, 5, 6, and 10. Yes, so 4, 5, 6, and 10. 10th group it is. That is nickel. The group starts with nickel, okay? Like I said, yeah, like I said, there are multiple factors here, right? So 3D series, there are multiple factors, 4D and 5D. So because of all these factors, the overall order that is coming out to be, it is this. And the same order we have for 10th group also. I'm not giving you the exact value here. And we cannot discuss that, each and every factor and what, see, if there are multiple factors, one factor gives you one particular order. Like for example, if I talk about the atomic size, simply, generally what happens, top to bottom increases. So 3D should have the maximum, then 4D, then 5D, ionization energy, it is this. But that is not happening in everyone, in all these groups, no? Because it's not like we have only extra shell it is getting added, right? In which subshell the electron is getting added, that is also a factor, right? The straining effect also a factor. And that is why lanthanide contraction comes into the part. Right, so based on all these factors, the overall order is coming out to be this. We cannot discuss this. Why for group 10, the order is this, right? It is basically, you can say, for group 10, you can say, since all the orbitals are for nickel, what is the order we have? It is 4s2 3d9, I guess, correct? 3d8, not 9. 3d8, right? So for below nickel, we have 5s2 4d8, and then we have 6s2 5d8. Like this, we have the configuration, right? So here what happens overall, the size, the electronic repulsion, I have given you the size order for 3D series. You must have seen initially it decreases, right? Then becomes almost equal, and then it becomes, then it increases, right? So size factor also we have a role over here. So overall, because we have multiple factors, so we cannot just say that what factors is dominating over here, right? Overall, all factors contributes into this ionization energy, and overall the ionization energy is coming out to be in this order. So this you have to memorize. One factor gives you one particular order, another gives you the another order, right? And the final result will be the mixture of the two, right? And that is how we'll get this. This you have to memorize. Okay. One thing is important here. Tell me, scandium belongs to which one? 3D series, we have scandium, and then we have yttrium, and then we have lanthanum. This is 3D, this is 4D, and this is 5D element we have. And all these belongs to group 3. So for group 3, the order is what? 5D is minimum. So order of ionization energy, if I write down here, we have minimum for lanthanum, then we have 4D, so yttrium, and then we have scandium. This one they have asked in the exam. Okay, this order you must remember. Now you write down the next thing here. The fourth point. For the same element, for the same element, electronic configuration, for the same element, electronic configuration is not considered no, lanthanum, we do not have lanthanide contraction. After lanthanum, we have lanthanides, no? So we have transition contraction into that, but still that factor is not that great. Okay, so what did I write? What did I say? For the same element, electronic configuration is not considered, but we consider the charge. Here also you'll understand that how two different factors, is present, and how it is contradictory also. I'll show you this. For the same element, suppose I'll give you an example of nitrogen N plus and N minus 3. Same element we have, that is nitrogen only. Okay. So if you look at the configuration of this, for nitrogen it is 2s2 2p3. For N plus it is 2s2 2p2. And for this one it is 2s2 2p6. So if you look at the electronic configuration, which one has maximum ionization energy? Which one has maximum ionization energy? N3 minus, correct, because it has fully filled configuration and then half filled and then unstable configuration, right? So EC, that is electronic configuration, gives the order as N minus 3, then N, and then N plus. If you talk about the charge on this, charge factor, right? we have minimum electron in this, N plus has maximum charge. The charge factor, you see, that's what I have given you. This, the size is for N plus is minimum. Then we have N, and then we have N minus 3. So size factor, if you're considering, or charge we don't write, we write here size. That would be better. Size factor, if you're considering, then the answer would be N plus would have the maximum electronic configuration, then N, and then N minus 3. Correct? So we are getting the reverse order here. Yes. So if suppose in the exam, someone thinks about this and someone thinks about this. Logically, electronic configuration disorder is correct. Size factor disorder is correct. But both of you won't get the correct, the correct answer into this, because only one is correct into this one. Right. So here the correct answer is, because we have the same element, then electronic configuration we won't consider, but we consider what? We consider size factor. And all these logic that is given, that why size factor is dominating, you can ask me this, why size you are taking, why not electronic configuration? There's no reason for this, right? Since the actual size is coming out to be in this order, that is N plus N and N3 minus, hence they said that size factor is the dominating factor. Did you get my point? So it's not like we have logic first and then we have the order. First, experimentally we determine the order, and then we say what logic satisfies this particular result, this particular order. And then we say this logic is the dominating factor we have. Did you get my point here? Right. So that's why in periodic properties or inorganic chemistry, you can think of, so why not this is happening? Why not this order? Right. In the book, the order and logic which is given, it is only the dominating logic and dominating factor we have. Okay. We can have multiple factors in one simple process. Correct? So we'll always talk about the dominating factor here. So size factor dominates whenever we have same element. We won't consider electronic configuration. That is what you have to keep in mind. Okay. Now, fourth, we have done. The fifth one, you see, boron family. The order of ionization energy for boron family, we know as we go down the group, ionization energy decreases. So it is boron, aluminium, gallium, indium, thallium. Right? All these questions that I'm giving you, all these questions they have asked in the exam, okay, previous year, whether it is NEET or JEE or any other BITSAT, any other exam, they have asked these questions, okay, because all these are exceptions we are doing, very important, okay. Boron, aluminium, gallium, indium, thallium. So this was the expected one, correct? This is the expected order we have. But this one again, it is not correct. Okay. See, I'm writing it down and then I'm crossing it so that you will understand this. Okay, that what is happening. This is not correct. The correct order is what? Correct order you have to memorize as 1, 5, 3, 2, 4. Okay. Decreasing order 1, 5, 3, 2, 4. These are the number of elements. 1 means boron, 5 means thallium, third is gallium, then aluminium, and then indium. right? In thallium, we have lanthanide contraction. Lanthanide contraction, okay? In gallium, we have transition contraction. In gallium, we have transition contraction. So 1, 5, 3, 2, 4, you must remember for boron family. Okay, group 13. Did you copy this? Carbon family, you see. Carbon family, the order is carbon maximum ionization energy order. Then we have silicon, down the group decreases, germanium, and then we have a change here, lead first, and then we have tin in the last. So we have a change here only in the last. That is because of lanthanide contraction. In lead, we have lanthanide contraction, and that's why the order is this. Okay, that's what you have to keep in mind. Always you see the lanthanide contraction comes into the picture for sixth period element, right? Because below that, fifth and all, we can have transition contraction. Okay, so these are the few exceptions of ionization energy. Okay, that you must remember. It's very important. Now, a few questions on this you see. Write down, arrange the following in increasing order of ionization energy. Question you see. Arrange the following in increasing order of ionization energy. Okay, write down the question. The first one we have Fe2 plus, Fe3 plus, and Fe. Mn2 plus, Mn, Mn4 plus, Mn plus 7, Mn plus 6. Try all these 4 questions. Finished? Done? Tell me. Okay. So the first one, if you see, positive charge increases means size decreases, and size decreases means difficult to remove an electron, and that's why the order of ionization energy is maximum for Fe3 plus because of size, simple. And same concept we have here for manganese. Mn is minimum, then we have Mn plus 2, Mn plus 4, Mn plus 6, Mn plus 7, right? O2 minus has the largest size, oxygen two minus has the minimum largest size, then O minus, and then O. This one I have already told you. You just have to remind the 3D series because it is group 3, and group 3 we know what is the order. For group 3 it is 3D maximum, then 4D, and then 5D. Okay, so 3D maximum, then 4D, and then 5D. 5D is lanthanum, 4D is yttrium, and 3D is scandium. So this is the order of ionization energy we have. Okay, so I hope all of you have done this. Now there are some facts for ionization energy. You write it down. There's 2-3 points we have here. There's 2 points we have. Facts about ionization energy. Write down the first point. In each period, alkali metal shows in each period, alkali metal shows the least ionization energy. the least ionization energy. Comma, write down cesium has minimum value of ionization energy, first ionization energy. Cesium has the maximum value of ionization energy, first ionization energy. Second point you write down.
Sir, could you repeat?
Okay, I'll repeat. In each period, alkali metal shows least ionization energy, comma, cesium. Cesium has minimum value of ionization energy. Cesium has minimum value of ionization energy. Second point, in each period, noble gas has highest ionization energy. In each period, noble gas has highest ionization energy. Comma, helium has maximum ionization energy. Done. When I say ionization energy, it means IE1. In a given period, cesium has minimum. Got to write this. IE1, noble gas has maximum value in a period and helium has maximum. Now you see one thing here. I have already told you that along any period, noble gas has the maximum radius. Yes or no? Why noble gas has maximum radius? Van der Waals radius, right? Maximum radius. So when you talk about this radius factor, then noble gas should have the minimum value of ionization energy, but that is not happening, right? It means what? In case of noble gas, we are considering electronic configuration, right? In case of noble gas, electronic configuration is the dominating factor over size, right? EC is the dominating factor over size, and hence we have the following order. But like I said, when you talk about this N3 minus and N plus, so here we are not considering the electronic configuration, but here we are considering the size factor, right? So I just summarize this, that if you have noble gas, then electronic configuration is a major factor. If you have the same element, then size is the major factor here. I hope you understood this. Okay. Next, write down the another term here, ionization energy we have done. We have seen all the exceptions. Write down electron gain enthalpy See here what happens. There is one more term here, that is electron affinity. Electron gain enthalpy and electron affinity. So both are different. There is a basic difference between the two, but they are not same. First of all, you understand that. Okay, they are not same. There's a basic difference between the two. Right, I'll discuss what is the difference, small difference we have there. Write down first of all the definition of it. The electron gain enthalpy. Write down, when an electron is added, I'll write down here just a second. When an electron is added to an isolated gaseous atom, to convert it into a negative, ion, then the enthalpy change in enthalpy, I'll write down, then the change in enthalpy in this process. The change in enthalpy is called electron gain enthalpy. You can say ionization enthalpy also, but that is not for removing an electron. Obviously, an atom, when you add an electron, it is converting into an ion. So it is because of addition, not of removal. So if you write ionization enthalpy, you'll get it confused from the previous concept. Right? So we are adding an electron here, not removing it. Okay. So electron gain enthalpy. Acha, one term I forgot to tell you in the previous one. Just one line you add in electron ionization enthalpy. That ionization enthalpy is always positive. Ionization enthalpy is always positive. Right? So this electron gain enthalpy that we have here, it is represented as delta Eg H naught. This is electron gain enthalpy. Okay, H naught, or simply we'll write like this, H negative on this, because we are adding an electron, so H negative. Right? This can be endothermic. You know this term, right? endothermic or exothermic, both. But the previous one, electron, just a second, Pratyup. Let me just give you some few points and then we'll discuss this. Okay, endothermic or exothermic means what? Endothermic means energy is getting consumed. Exothermic means energy is getting released. Right? One more point you write down. It gives us an idea. It gives us an idea that how easily it gives us an idea that how easily an atom can accept electron. Right? It gives us an idea that how easily an atom can accept an electron. Okay, next point. All these points are very important. Okay, write down this point first. Next one. The negative electron gain enthalpy means electron gain enthalpy, you can write down the symbol delta Eg H negative. Negative electron gain enthalpy means the energy releases in this process. Releases in this process. So this means what? Suppose we have an atom A, gaseous atom, and we add an electron onto this. It converts into A gas negative ion, and some energy comes out into this delta H1. Suppose we have energy comes out in this process. Obviously, this value is negative. Suppose I am assuming this to be as, like, just a second, I'll write down. Another atom Bg gas plus electron, if you add, it converts into Bg minus plus some energy comes out in this process also. So this value is mostly negative. I won't say that it cannot be positive. It can be positive, but mostly it is negative only. So suppose we have 10 kilojoule of energy we have here. And this is suppose we have minus 20 kilojoule of energy. So this negative sign represents that the energy is getting released, right? Negative means the energy is getting released. If you have to, compare the energy in exchange in these two reaction, in these two processes, we can say obviously the delta H2 is more than the delta H1 because we'll compare only magnitude in order to understand the exchange in energy. Because the negative term, it just means that the energy is either getting released or getting consumed. Okay, so negative means energy is getting released. If it is positive means energy is getting consumed. Right? So that is what the one thing. Another thing is what? The one which releases more energy, it means it can easily gain that electron. Right? Means electron gain enthalpy of B is more than to that of A. Just for an example, I've told you. Like I said, it can be positive also. Now, what do you mean by this? Suppose you have an atom. What do you mean by enthalpy change? Correct. You have an atom, and obviously the atom has certain electrons present into it, inner shell electrons. Right. So we have inner shell electrons present here, right? And you are trying to add an electron, extra electron onto this. What happens? This atom is neutral. Right? This is the neutral. And you are trying to disturb its neutrality. You're trying to convert this atom into an anion, negative charge ion. So obviously this do not want to go into the negative ion phase, like don't want to accept an electron easily. Because the inner electrons would definitely repel the coming electrons onto the surface. Right? So this acceptance of electron depends upon its configuration or the distribution of electron in an atom. Sometimes it is very easily it will accept. Like for example, if you have this one, what we say, carbon, right? Carbon, the electronic configuration is 1s2, 2s2, 2p2, right? This wants to gain an electron and to convert into half filled configuration. That is the more stable configuration. If you talk about nitrogen, right? So 1s2, 2s2, 2p, sorry, not nitrogen, it is chlorine. 1s2, 2s2, 2p5. This also has high tendency to accept an electron and convert into a negative ion so that it has the noble gas configuration. So depending upon the electronic configuration, atom has tendency to accept an electron in an easier way or in a different way. Like you have to push the electron also sometimes. You got my point? Okay, so that is how the exchange in energy takes place, because we have electron-electron interaction. So there will be some change in the position of an electron from one orbital to another orbital. It is may be possible. So because of that change in position or potential energy, some energy either releases or gets consumed. So that is the enthalpy change we have. Right? So for all these elements you see, the electron gain enthalpy is negative. And negative means what? Energy releases. It will take that electron and release some energy. Go to the lower energy state, it becomes more stable. But in case of noble gas, the electrons which enters into the noble gas, it goes to the higher energy level because lower energy is already filled, completely filled configuration. So in case of noble gas, the electron gain enthalpy is positive. Means we have to push that electron. Like forcefully, you have to add this electron onto the noble gas, because noble gas is already neutral. Neutral plus it has a stable configuration. All orbitals are filled. And then again, you want to add an electron onto it. So you have to push that electron onto the noble gas. So in that case, you have to provide energy from outside so that the electrons enters into the orbital of noble gas. So that process is endothermic process. So only for noble gas it is endothermic, otherwise it is exothermic. Okay, so write down this point. Write down these points. Halogen has very high negative electron gain enthalpy. Halogen has very high negative electron gain enthalpy. Negative electron gain enthalpy. Since it has high tendency, since they have high tendency to accept one electron and gains noble gas configuration. Write down. On the other hand, next line, on the other hand, noble gas have large noble gas has large positive electron gain enthalpy, as large positive electron gain enthalpy. Noble gas has large positive electron gain enthalpy, already stable, already stable, already stable, already stable, and electron has to enter. Yeah, I'll repeat. Let me finish this first. An electron has to enter into the next higher energy shell. Next higher energy shell. I'll repeat it. On the other hand, noble gas have large positive electron gain enthalpy, large positive electron gain enthalpy, large positive electron gain enthalpy, because the electron has to enter into the next higher shell, because the electron has to enter into the next higher shell, correct? So must keep that in mind, that electron gain enthalpy can be positive, can be negative. Positive means it is gaining energy from outside. We are providing energy into it. Negative means it is releasing energy. Sign just means the exchange of energy, whether the energy is getting consumed or energy is getting released. If you have to compare the electron gain enthalpy, we just compare the magnitude. We don't compare the sign. Just will compare the magnitude, right? Next. Write down into this. Next line, write down electron affinity. Electron affinity is the tendency of an atom electron affinity is the tendency of an atom to accept electron. Right? Tendency to accept an electron. It is defined at absolute zero temperature. It is defined at absolute zero temperature. The relation is, this relation you write down, the electron gain enthalpy E delta Eg H negative is equals to the electron affinity, that is EA, is the electron affinity minus 5 by 2 RT. This is the relation we have. Of electron gain enthalpy and electron affinity. Not much important, but this is the relation we have. Right, so electron gain enthalpy is what? It is slightly higher than the electron affinity, right? When, if it is absolute, see actually what happens, if you take this condition here, absolute zero temperature. What is absolute zero temperature? absolute zero temperature is 0 Kelvin, right? 0 Kelvin, which means minus 273 degrees Celsius. You see this low the temperature is. So at this temperature, we do not have any kind of motion in the molecule. Even vibratory motion is also not there. Okay, the atoms or any for any object, the all kind of motions are ceased, right? No vibratory motion is there. That temperature we call it as absolute zero temperature, which is practically, it's difficult to achieve absolute zero temperature. So when you substitute this here, the electron affinity, it becomes negative of delta Eg H negative. That's why in some book they have written this, that electron affinity is what? It is the negative of electron gain enthalpy. Yes, it is a hypothetical number, right, value, but it is very difficult to achieve. We won't say that we cannot achieve it, but yes, it is very difficult to achieve, minus 273 degrees Celsius. Okay. So electron affinity is minus delta G H naught. That's why we say that electron affinity is negative of electron gain enthalpy, which is not always true, right? Because the actual relation is this. Okay. Now the variation, the trend of electron gain enthalpy, you write down. The first point, as we go down the group, top to bottom, delta Eg H naught, electron gain enthalpy, decreases. In a period left to right, if you go, delta Eg H naught increases. The reason is, left to right, if you go, size decreases, atoms becomes smaller, and it is easier to add an electron onto the smaller atoms because we have more electrostatic pull, right, towards the nucleus. So size, the reason for the second point is what? Z effective increases, size decreases, and it is easier to add an electron on a smaller atom. Other way, if you think top to bottom, you are going, size increases, difficult to add an electron. That's why delta Eg negative decreases. I didn't get you, Pradyun. What other elements? Oh, that depends. I'll tell the trend here. The trend is this only. Left to right, it increases. Means negative value increases. So extremely, the immediate left to it that you have, it has slightly lesser negative value than the immediate right one. Negative value. Okay, I'm not talking about magnitude. Negative value, which means the same actually. One more thing you must take care of. More negative. Just a second, Pradeep. More negative delta Eg H negative, more negative electron gain enthalpy means it is easier to add an electron on that particular atom. Right, more negative value means easier to add an electron on that particular atom. Right on this point, more negative electron gain enthalpy, more negative electron gain enthalpy means tendency to accept electron is more. Okay. Now, factors of it, you see, factors affecting it. First point, write down size of an atom. Size of an atom is more, it is difficult to add an electron, hence it is inversely proportional. More energy is required. Okay, so delta EGH negative is directly proportional to 1 by the size of an atom, atomic size. Second point, effective nuclear charge, Z effective. As Z effective is more, then delta H negative is also more. Okay, so what we can write, Z effective is directly proportional to this. More value of Z effective, more will be the attraction towards the nucleus, and more will have the tendency to accept an electron. Third one is electronic configuration. Electronic configuration, write down in this, elements with half filled or fulfilled orbitals are more stable elements with half filled or fulfilled configuration has less tendency to accept, write down like this, or fulfilled configuration is more stable and has less tendency to accept an electron. Okay. Okay, this is what you have to keep in mind. Now, write down next one. This is the three factors we have. Okay, this must keep in mind. Few exceptions we have into this. I'll just tell you the exceptions. Yes. Okay. So you write down first of all trend here. Trend I have given you already. No? Just a second. Trend I have given you already. That's let it be. Okay. Write down exceptions. The last thing here. Exceptions. Okay. Write down the first point. For group 14, group 14, 15, 16, and 17, the value of electron affinity, the value of electron affinity okay, the value of electron gain enthalpy for second period element is lesser than lesser than lesser than the third period element because in P2 subshell, P2 means period 2, because in P2 second period the elements, because in P2 elements electrons goes into second shell, which is relatively smaller or relatively small, and hence produces significant repulsion. Repulsion means to the coming electron that we are trying to add. Okay, that's why its electron gain enthalpy is less. To some extent, it is true for group 13 also. Like you see, nitrogen has lesser electron gain enthalpy than phosphorus. Oxygen has lesser than sulfur, right? Fluorine has lesser than chlorine. finished. One last point we'll see into this one. For group 17, this is the most important one. You'll get this question in the exam. Chlorine has maximum electron gain enthalpy, then fluorine, then bromine, and then iodine. If you talk about for group 16, it has more irregular trend. Sulfur, it shows it is maximum for sulfur. Just a second. Hello. Yeah, hello. Sorry, I got a call. Actually, important it was. 1 second. So, yeah. So, what I was talking about, group 16, right? Sulfur, selenium, tellurium, and oxygen. This is the minimum. So these two, trends for electron affinity is the most important one. This question they have asked many a times in the exam. In fact, chlorine is the element which has the maximum electron affinity, like among all the elements present in the periodic table. Okay, so like we have few facts that you should memorize, and I'll give you here. Write down the first point. It's overall actually electron ionization enthalpy plus this electron gain enthalpy. Write down the first point. Maximum electron affinity. Write down like this. Maximum electron affinity, which means the one which has the maximum electron affinity, this is the most reactive non-metal, because the maximum electron affinity, it has tendency to accept electron, right? So most reactive non-metal, and this is chlorine. This is the one thing that you must memorize. Now the next thing is minimum ionization energy. Minimum ionization energy is for the most reactive metal. For the most reactive metal, and that is cesium. Minimum ionization energy, right? The element which has maximum ionization energy and minimum electron affinity and minimum electron affinity is the most unreactive non-metal. You see, these are three different terms. Most unreactive non-metals, that is the inert gas. These two things you must memorize. In fact, the electron affinity of chlorium, the last point here, the electron affinity of chlorine, Cl, right? Maximum electron affinity. It is in fact lesser than the minimum ionization energy, that is for cesium. So cesium has minimum ionization energy. So minimum value of ionization energy is, even it is greater than the maximum electron affinity of chlorine. These are the few things that you have to memorize. Theoretical questions they may ask you on this. All these are factual, okay, the values based order that we have here. Okay. So one thing is left, we have already done, but there are few properties we can conclude on the basis of ionization energy and electron affinity. So what are those properties? We'll discuss that after the break. Okay. So take a break now. We'll resume the session at 6:35. Okay. Take a break. Few properties based on ionization energy and electron affinity we'll see. Take a break. 6:35 will resume. Yeah. After the break, Oshi, correct? We'll discuss it after the break. Hello. Yeah, can you hear me? So we have discussed ionization energy and electron gain enthalpy, electron affinity, correct? Okay. Now, few properties that is related to these two things, like we'll discuss that later also. Like tendency to lose electron is nothing but the metallic nature, right? Metallic property. Metallic property is what? Is the tendency to lose electron, correct? So the elements which has low ionization energy can easily lose electron, right? The elements with low ionization energy can easily lose electron, and hence it is metallic in nature, right? So we can easily compare the metallic behavior with the help of electron ionization enthalpy, right? So what we can write here, you see, the elements with low ionization energy, elements with low ionization energy, what we can say, they are metallic in nature, because metallic property is nothing but tendency to lose electron, and when they loses electron, they are electropositive also. Tendency to gain electron is electronegativity, lose electron is electropositivity. Losing electron, hence they are a reducing agent. Reducing agent, basic in nature, basic in nature, and forms ionic compound. All these property we can conclude from ionization energy. Got it? This thing will use in other chapters also in organic chemistry when we do this. Okay. So the next thing we have to discuss here is electronegativity. Write down the heading, electronegativity. We have discussed it once in general organic chemistry. So briefly we'll go through it here. Heading, you write down electronegativity. Write down, electronegativity is the tendency of an atom to attract shared pair of electron. To attract shared pair of electrons, towards itself, in a covalent bonded molecules, in a covalent molecule. Right? In a covalent molecule. Little bit of idea I guess you already have for electronegativity. Okay. There are formulas by which we can calculate electronegativity for any element. Okay. However, in the exam, test, or in JEE, they won't ask you to calculate it. Okay. Trend of electronegativity, you should know. What is electronegativity? You should know. And what are the electronegative elements we have in our syllabus? Those things you should understand. They won't ask you to calculate the electronegativity of an atom. Okay. But yes, we'll see that formula. Right. So electronegativity, you cannot associate this with electron gain enthalpy, because electron gain enthalpy is is defined in gaseous state, but electronegativity is in bonded state, covalent molecule we have. Shared pair of electron it attracts, right? So that's why we cannot compare this, or there is no similarity between electronegativity and electron gain enthalpy. Suppose what happens, we have a molecule, covalent molecule AB. Okay, we have a covalent molecule AB, right? So this is the electron pair we have between A and B, right? So what happens, the pair of electron bond pair is more, inclined, or we can say it is shifted towards the more electronegative atom. This is the electron density I am representing it here. This is true when electronegativity of B is more than to that of A. So shifting of electron, like if you remember, I have just already discussed it, that it is a tug of war between A and B, right? A and B if you have, so A will have the electron density if the electronegativity of A is more than to that of B. Okay, this is electronegative, shared pair of electron. Okay. Now, the factors which affects electronegativity are factors you write down. First one, as Z effective increases, electronegativity En increases. More tendency to attract an electron. Okay. Atomic radius increases. Radius increases. Electronegativity decreases. Okay. That's why top to bottom, if you go top to bottom, electronegativity decreases. Left to right, if you go in a periodic table, okay, left to right, if you go, electronegativity increases. Third point, if the positive charge on atom increases, electronegativity increases. Because of positive charge, it will attract the shared pair of electron, and hence electronegativity increases. Okay. Now, fourth one is hybridization. If you remember, we have also discussed this. The concept of hybridization we'll discuss in chemical bonding in detail. But in this GOC, we have discussed as percentage S character increases, hybridization, electronegativity increases. Electronegativity increases. Like we know, sp hybridized carbon has maximum electronegativity, then sp2 and then sp3. Do you remember this? Yes. In GOC we have discussed it, right? So this is also we have here, right? Okay. Now, to measure electronegativity, how do we find out electronegativity between the two atoms? We have 2-3 formulas. Okay.
Sir, could you go back one sec, the last slide?
Just a second.
Thank you, sir. Sorry. Okay.
Done?
Yes.
Okay. So how to measure electronegativity? Like I said, hardly they'll ask you this question. But we'll see those, the two formula we have here to measure electronegativity. And the formula we have, the first one is Pauling's scale. Paulings. Pauling's scale. The formula is the change in electronegativity. We'll find out by the formula, which is 0.208 root over of delta AB. Delta AB. Delta AB is what? Delta AB is the energy. Resonance energy is the term. It is the energy involved in this particular molecule. Resonance energy. Okay, we don't have to bother with this resonance energy over here. You just need to know how to find out this delta AB. Delta AB is equals to energy associated with the bond AB minus root over of it, energy associated with the bond AA, and energy associated with the bond BB. If they ask you to find out the change in electronegativity or the electronegativity difference between A and B, so you have to use this formula. All these values will be given in the question. You don't have to worry about it. Just you need to find out delta AB, substitute it here, you'll get the answer. But like I said, hardly 1%, probability is also not there. Hardly they'll ask you to calculate the electronegativity. Okay. On this Pauling scale, okay, Pauling was a scientist. He calculated the electronegativity for various elements. And the order that we get here, write down electronegativity order. Is fluorine, then oxygen, then nitrogen. Chlorine, bromine, iodine, then sulfur, all these elements. These three you must remember. These three. To some extent, you will be required this chlorine also, but these three you must remember. Okay. Fluorine is the most electronegative element. And according to Pauling's scale, the electronegativity of fluorine is 4. According to Pauling's scale, the electronegativity of fluorine is 4. Okay, done. Done. Tell me. There is one more formula. We call it as Mulliken scale. Mulliken scale. According to Mulliken scale, the electronegativity is defined as the average of ionization potential and electron affinity divided by 2. Okay, so it is the average of the two values. Okay, just the formula. Sometimes they'll ask you, according to Mulliken, what is the formula of electronegativity? And they'll give you different form here. Like, you can cross multiply and write down the another form of it, like ionization potential. They can ask you like this. According to Mulliken, what is the ionization potential? It will be 2 times electronegativity minus electron affinity. Like this also they frame sometimes the equation and they'll give you 4 different options. Okay, just the formula you need to know. Okay, now the application of electronegativity, this is important, write down. Application of electronegativity. Okay, so first one is, the first one is naming of compounds. Write down in a compound, okay, naming of compound, write down the in a compound, the more electronegative atom, more electronegative atom must be written in the last with "ide" suffix. With "ide" suffix. For example, you see this. If you write down IBr, what is the name of this compound? If you write down Cl2O, yes. So bromine is more electronegative, right? So it is iodine bromide. Okay. oxygen is more electronegative, so dichloroxide, ide suffix we are adding. That's what one of the application we have, nomenclature of compounds. Okay. Okay. Second one, you write down nature of bond.
Sir, could you just go back to the
Just a
previous?
second. Just a second. Just let me write down the heading, nature of bond. Done? Okay. The next one is write down the nature of bond. Write down if the difference in electronegativity if the difference in electronegativity between the atoms present in a bond is less than 1.7, between the atoms present in a bond is less than 1.7, then the bond is covalent. And if it is more than 1.7, it is ionic. Okay. If the chain difference in electronegativity is less than 1.7, it is covalent. If it is more than 1.7, it is ionic. Okay. So here we have an exception, the exception of HF. HF. Okay. If you find out the change in electronegativity, right? It is the electronegativity of fluorine minus to that of hydrogen, which is 2.1. This is the value I am giving you. So this is 1.9. So according to this theory, the bond between H and F must be ionic, but it is covalent in nature. Actually, it is covalent. Right. This is an exception. Okay. We can also calculate the ionic character in covalent bond. Okay. What do you mean by this? We'll discuss that. So next, write down ionic character in covalent bond. We'll find out percentage ionic character by this formula. This is equals to 16 into delta of change in electronegativity plus 3.5 into change in electronegativity square. This is the formula. Now the thing is, what do we understand with this ionic character in covalent bond? See, first of all, any molecule we have A and B, two different atoms if it is present, then we must have some difference in electronegativity between A and B, right? Depending upon this difference, okay? So if the difference between the electronegativity of A and B, like I said, if it is more than 1.7, it is ionic, otherwise it is covalent, right? So whenever we have a molecule which has two different atoms, so we must have more or less ionic or covalent character, right? Right. We cannot say a given molecule which has two different atoms is completely ionic or completely covalent. When I say HF is covalent molecule, it means its ionic character is less. That is what we can say in other way, right? When I say a molecule is covalent, means it has less ionic character. That is what it means. But yes, a covalent molecule has certain or few ionic character also. And we always talk about the dominant, character for the bond. But if you see a molecules like Cl2, so we do not have any electronegativity difference. Delta En is equals to 0. So this one is completely covalent. H2, delta En, 0. This one is completely covalent. But when we have HCl, when we have HF, right? When we have any other example you take, H2O. So we must have some difference in electronegativity between the atom present in the molecule, and hence it will neither have 100% covalent character nor 100% ionic character. So in that case, we sometimes calculate the ionic character in covalent bond with this formula. Okay. Again, this formula is, you will use this rarely, because if they ask you to find out ionic character in a covalent bond, they must give you the electronegativity value of the atoms present in that particular bond, because you cannot memorize the electronegativity value for all the atoms. Okay, that's why these formulas are not important. Later on, we'll see this, that in a covalent bond, the ionic character we can understand uh, with with other values also that we'll discuss. Okay, but not that important. In ionic bond also, we can understand simply that what covalent character is, how much covalent character is, right? So it's both way it goes. In a covalent bond, we have certain ionic character. In ionic bond also, we have certain covalent character, right? So that part is important. The second one that I discussed just now, we'll discuss that later, how to understand the covalent behavior in an ionic molecule. Okay, this is the formula. Now the next one is third one is bond length. Bond length and bond strength. I'll do this in one only. Bond length and bond strength. See, bond length and bond strength, first of all, these are inversely proportional. If bond length is more, bond strength is less. Bond strength is more, bond length is less. So bond length BL and bond strength BS are inversely proportional, first of all, right? Okay. What is the relation with electronegativity? So write down, as electronegativity difference increases, bond length decreases. Right? As electronegativity difference increases, bond length decreases. See, we also have a formula. The bond length, if you need to find out for DAB, again, this formula is also not useful. We won't use all this formula. Radius of an atom A plus radius of an atom B minus, we have 0.09 change in electronegativity. So obviously, if this is more, the bond length less. This one is the bond length. Okay. So again, I'm repeating this thing again and again. You don't have to bother with all this formula from where it comes and all. There's no, the derivation of it is just based on the facts and uh, they have given hit and trial method they have used, and they have given these kinds of formula. So no derivation, nothing is there, so you don't have to bother with this, right? So this is, you see, as electronegativity difference increases, this value increases, hence bond length decreases. So bond length decreases, so bond strength increases. So what we can write, the change in electronegativity here, delta En, is directly proportional to bond strength and inversely proportional to bond length. So if I ask you, what is the order of bond strength of HF, HCl, HBr, and HI? Done? Bond length is this. If bond length is this, then bond strength is opposite. Bond strength is this. Now you see bond strength of HI is minimum, right? It means what? You can easily break this bond and H plus can go out, right? It means this molecule can easily donate H plus ion. Relatively, I'm talking about, relatively among the four, right? This has the max tendency to release H plus. Hence, the acidic order, if you see, the acidity order of HI is max, right? So HI is most acidic, HF is the least acidic compound. So you see this here. This is the acidity order also. Done? Oh, I'm sorry, just a second. Yeah. No, HF is the least acidic we have. HI is the most acidic, then HBr, then HCl, then HF. Okay. Now, the next one you see, Write down dipole moment. Dipole moment is represented by mu. Okay, so if you see, we have two charges present at a very small distance, q1, q2, positive, negative charge. At a distance d, okay. So the dipole moment here mu is equals to q cross d, where q is the charge. This is the charge, and this dipole moment is the vector quantity. Direction of this dipole moment is from positive charge, positive to negative. Remember, in physics it is opposite. In physics it is negative to positive, but in chemistry we take it as positive to negative. Okay, so it is a vector quantity, positive to negative, q times d we define it as. Okay, so vector quantity is this. Okay, so in a molecule, suppose we have HCl. This concept we'll use in organic chemistry also when we talk about polar and non-polar solvent. Suppose we have HCl. Chlorine is more electronegative, delta negative. And this is delta positive. So because of this charge, plus and minus, we'll have again a dipole moment from positive to negative, represented by this line, right? Dipole moment. And this molecule has net dipole moment, which is equals to the charge over here, Q, and the bond length, that is D. This is the bond length here. So because of the electronegativity difference, we have charge separation in the bond, and obviously we have some bond length there. So that charge separation into the bond length gives you the dipole moment of that particular bond. Like I said, it's a vector quantity, always from positive to negative. But again, we don't have to calculate dipole moment in a given molecule. But just we have to get an idea whether this dipole moment is zero or whether this dipole moment is non-zero. Right? If the dipole moment is zero, the molecule is said to be non-polar. Right? If dipole moment is non-zero, it is said to be polar. Molecule is said to be polar. These 2 points you must remember. Okay? So just you need to understand this, whether not required, Kshitish. Like I said, you don't have to find out the exact value of dipole moment here. Okay, Q you don't have to find out. Just you need to know that whether there is dipole moment or not, equal to zero or not equal to zero. Just that. Okay. For example, I'll give you some example here. Suppose we have BeCl2. BeCl2. Suppose we have BF3. Okay. One more we see. H2O. in these three molecules, you see which one is polar and non-polar. Done. See, to understand this, you should know the geometry of this molecule, means the structure basically. So BeCl2 is linear. And how do we know this? We'll study this in chemical bonding. Okay. When we do chemical bonding, you'll have the idea that how the structure of a molecule can determine. BF3 molecule is trigonal planar. It is this. Okay. H2O is bent shape, which is this. Now you see chlorine is more electronegative, delta negative, delta negative. Fluorine is more electronegative. Oxygen is more electronegative. Right? It is delta positive, delta positive, delta positive, and delta positive. Now, because of this charge separation, we have dipole moment in this molecule. Suppose this one we have positive to negative in this direction because of this bond, and because of this one we have dipole moment in this direction. So you don't have to calculate the value here, like I said. Okay, since it is a vector quantity, so these two cancels out each other, right? So for this molecule, we can say mu is equals to 0, and when mu is 0, it is non-polar. For this one, you see, we have dipole moment in this direction, dipole moment in this direction. And for this bond, we have dipole moment positive to negative in this direction. So for these two, we have resultant in this direction. For of these two dipole moment, you must have studied vector, right? Yeah. Any doubt in this? Okay. So resultant of these two vectors we have in this direction, and this one cancels out each other. Hence, the dipole moment of BF3 is also 0, and it is non-polar. H2O, if you see, positive to negative, and it has net dipole moment in this direction, this is mu net, and hence net dipole moment is not equals to 0, and it is polar in. Done, all of you? Okay. The next one you see, Write down the heading, polarization. Okay, write down the theory here, 2-3 lines, and then we'll discuss. Right, polarization is defined in ionic bond. Right? It is a property of ionic bond, defined in ionic bond. Write down, whenever whenever a cation whenever a cation approaches an anion, when, whenever a cation approaches an anion, then there is tendency, in there is tendency of, you write down, there is tendency of distortion of in electron cloud. There is tendency of distortion of electron cloud of anion. There is tendency of distortion of electron cloud of anion. I'll explain this. First, you write down. Okay, again, I'm repeating this. There's tendency of distortion of electron cloud of anion. Yeah, just a second, I'm repeating it. Whenever a cation approaches an anion, there's tendency of distortion of electron cloud of anion. Okay, next line you write down. The tendency of cation to distort the tendency of cation to distort the electron cloud of anion okay, the tendency of cation to distort electron cloud of anion is called polarizing power. Okay, it's called polarizing power. Okay, again I'm repeating this. The tendency of cation to distort the electron cloud of anion is called its polarizing power. Again, next line. The tendency of an anion to get its electron cloud distorted the tendency of an anion to get its electron cloud distorted is called its polarizability. Okay, the tendency of an ion to get its electron cloud distorted is called its polarizability. Okay. Next line, this phenomenon of distortion of electron cloud is called polarization. This phenomenon of distortion of electron cloud is called polarization. It's called polarization. Now, what is polarization? You see, suppose you have all, why it is a characteristics of an ionic bond, because we need charge, right? See this. Suppose we have a cation, positive charge, and we have an anion. So when these two comes closer, right, then what happens? This positive charge attracts this electron cloud, right? Because positive negative will have the attraction. So what happens? This positive, this negative charge, it won't be a sphere, a complete sphere it won't be, but it will be distorted. So after sometimes what happens, since it starts attracting towards the positive charge, right? So after sometimes there will be an interaction, and this negative charge, it goes like this. It comes like this, negative charge. So this distortion in the electron cloud, we call it as polarization. You got my point? Tell me, did you understand it? So because of positive negative attraction, the electron cloud starts shifting onto the positive side like this. So electron cloud get distorted here. So the ability of this positive charge to distort the electron cloud, it's the polarizability of this cation. So polarizability is defined for the cation, the ability for this electron to get, sorry, other way it is, the tendency of a cation to produce this polarization is called its polarizing power. So polarizing power is for cation. The ability of this electron cloud to get distorted is called polarizability of this anion. So polarizability is defined for anion, polarizing power is for cation, and this phenomenon of distortion, we call it as polarization. Now you see, electron cloud is nothing but the electrons. See, when you write Al3 minus, correct? Suppose this one you write. This 3 electron which is present around this aluminum surface. So it is the electron cloud we have. It is basically the electron that moves around any atom. The electron is electron cloud. So it is just an the charge density. You can say electron density. The term we use electron cloud, nothing much. You got my point? Now you see one thing here. What is ionic bond? Ionic bond is because of the attraction between the positive and negative charge. Suppose we have NaCl. So we have Na plus and Cl minus. So it is the ionic bond because you have electrostatic attraction. When the charge density is decreasing, because if this charge starts spreading between the 2 points here, then it leads to what? It leads to covalent character. Yes or no? Tell me, guys. If we have 2 point charge, plus and minus, this is ionic. But when you start distributing this charge between the 2 point here, then obviously we can say the ionic characteristics is decreasing and covalent characteristics is increasing. Yes or no? Can we say that? Because of polarization, ionic character decreases and covalent character increases. Okay. So this theory is given by a scientist called Fazans. And this we call it as Fazan's rule. Fazan's rule. Okay. What is this rule? One is line just you write down. It explains the covalent character. It explains covalent character in ionic compound. It explains covalent character in ionic compound. One last line you write down. Polarization leads to covalent character. Polarization leads to covalent character in ionic molecule. Polarization leads to covalent character in ionic molecule. There are a few more things left in this Fazan's rule. Okay, so that will continue from this next class. Okay, so just remind me, we have to do Fazan's rule. Okay, so we'll continue from this next class. Okay, so there are no 2-3 things left in this chapter, and then we'll uh, uh, finish this off in the next class in 1 hour probably, and then we'll start with the next chapter, that is probably more concept 2. Okay, fine. Thank you guys. I'll send the assignment on this. You can give it a try. On Learnist also the assignment has been uploaded. That also you can try. Okay. Thank you guys. Take care. Bye.